With theoretical probability, you're measuring the chance of a certain event occurring in any trial of an experiment. Remember, this is based on what we theoretically expect to occur. If I flip a coin, I'm assuming what's going to happen is I'm going to get heads 50% of the time and a tails 50% of the time. In general, your probability of an event A happening is the number of trials or the number of members in event A divided by the total number of possible outcomes. And this is given to you in the formula booklet. Complementary events. Let's say you roll a six-sided die. If I look at the probability of getting a 6, again, theoretical probability, there's only 1 6 on that die. So my chance of getting a 6, my probability of getting a 6 would be 1 out of all 6 sides. The probability of not getting a 6, I could roll a 1, a 2, 3, 4, or 5. So I'm looking at 5 out of 6 probability, or whatever those decimals are. And if you notice, if I take the probability of getting a 6 and the probability of not getting a 6 and add them together, I get 1. So getting a 6 and not getting a 6 are complementary events where one of them must occur. I'm either getting a 6 or I'm not getting a 6 when I roll that die. So taking that to the general piece, if A is an event, then A with the apostrophe is the complementary event of A. And just like how we saw with the die in the previous slide, the probability of A plus the probability of not A equals 1, or the probability of not A is the same thing as 1 minus the probability of A happening. Our final example 2, consider rolling a six-sided die. What's the probability of getting a result of 4 or more? So six-sided die means that my denominator is going to be 6. 4 or more means I can get a 4, a 5, or a 6. So I'm looking at 3 of those 6 sides. And again, either simplifying the fraction or writing it as a decimal. Part B, a card is drawn from a standard deck of 52 playing cards. We're first being asked to find the probability of drawing a diamond. So if you don't know, standard deck has 4 different suits: diamonds, hearts, spades, and clubs, and they're split equally. So that means pulling a diamond, there are 13 diamonds of the 52 cards, or I'm looking at 1/4 of the cards being diamonds. So I have a 1 in 4 chance of drawing one. Probably of not getting a diamond, I'm looking at any of the other 3 suits. So again, I can just use the formula that 1 minus the probability of getting a diamond will get me the probability of not getting a diamond, so 3/4. All right, and our last slide here, just a piece of practice. So pause the video, try it on your own, and come back for the answers. When you're finding the expected number of times that a die will show whichever question you're looking at, you're taking the probability, multiplying it by the number of trials. So what I've done for all 3 of them for now is just listed out what the probability is. So if I'm looking at a factor of 12, that means I'm looking at 1, 2, 3, 4, 6, and 12. So that's 6 different times out of my 12 numbers that I'll get a factor of 12. And then I'll multiply that by the total number of times the die was thrown, which is 154. And when I do that, I get 77. So I'm expecting to see a factor of 12, 77 out of the 154 times. With my prime numbers, 2, 3, 5, 7, and 11 are all prime numbers. Remember, prime has to have 2 distinct factors, 1 and itself, which is why 1 is not included. So it's 5 numbers out of the 12, multiplied again by 154, means I'm looking at 64.2 times, or you could round that either down or up to 64 or 65 times. Remember, this is just an estimate, so if you leave it as a decimal, that's fine too. And then finally, prime factor of 12. So I had 2 of those prime numbers that were also factors of 12, 2 and 3. So 2 out of my 12 numbers are prime factors of 12, and I'm multiplying that one more time by 154 to get 25.6 repeating. So to three sig figs, 25.7, or again, rounding it down to 25 or up to 26 is fine.